Welcome to part 3 of two-dimensional autonomous systems. This exercise is something we are going to revisit now because we were able to find the solutions, specifically solutions for these initial conditions as given here, by first computing the eigenvalues and eigenvectors and basically applying the eigenvalue method, writing the solution as a linear combination of the eigenvectors of this matrix, which has 2 rows and 2 columns. And one thing that we were able to notice was that those solutions had both non-zero real parts and non-zero imaginary parts. Specifically, we had found that x1, the solution vector, is the vector of state variables called x of t, okay? And we had specifically found that x of t has entries x1 and x2. x1 is written as 8 et cosine of 2t minus I2 et sine of 2t. So that first entry has a real part and an imaginary part, and so does the second entry. So we're going to construct solutions for general solutions for this problem. We're going to ignore the initial conditions for a minute, and we're going to construct general solutions such that these solutions have 0 imaginary parts. In other words, we're going to do a technique to get rid of the non-zero imaginary parts. The first thing is we would like to remember that we have a complex, so remember, let z be a complex number. So that means that we can write this complex number as the real part plus the imaginary part, and also means that the conjugate of this complex number is written as real part minus I times the imaginary part of this number. So if we add both the number and its conjugate, what you will notice is that by definition, adding up those two numbers, the imaginary parts get cancelled. So we end up with something that looks like 2 times the real part of the complex number, and this very easily implies that if we divide both of these quantities by 2, we end up with z plus conjugate of z divided by 2. That's exactly an expression for the real part of this complex number. And you possibly can see now a pattern. We can do a very similar thing to have an expression for the imaginary part of the complex number. So let's do that next. So if we compute the complex number minus its conjugate, would be subtracting the conjugate from the complex number. The real parts will cancel. This minus I imaginary of z will become positive, and we will end up here with 2i times the imaginary part of the complex number. We divide in both sides by 2i, so we have z minus the conjugate divided by 2i, and this would give an expression for the imaginary part of the complex number. So all this is defined in terms of scalars, but it turns out we can apply something very similar for vectors. So we're going to construct new solutions given the solutions we had used before. Okay, so we're going to use those eigenvectors v1 and v2, and from them we're going to construct new solutions in such a way that we're going to get rid of the imaginary parts. Everything involved will have real parts only, and we're going to apply exactly this technique. So first we're going to define, we're going to give some names. Well, these are kind of the names we already had. So we're going to say, okay, let so we're going to use z sub 1 and z sub 2 for vectors, and we're going to define this vector e lambda 1t times vector v1. We're going to call that z1. And we're also going to let z2 to be defined as the conjugate vector, the conjugate of vector z1. Okay, so here we'll see that this becomes e to the t times e to the I 2t times v1, which is a vector with entries 1 and minus I. As for the vector z2, we'll be taking the conjugate of precisely this vector, and the conjugate of et would be exactly e to the t. The conjugate of e to the I 2t would be minus e to the minus I 2t, and the conjugate of this vector would be 1i. So we're going to define a new vector, and this is something we'll need for this new solution. We're constructing a new vector z3, which is given by z1 plus its conjugate. Okay, z1 plus conjugate of z1 divided by 2, and that's directly with the intention of using what we had quoted before from what happens at the scalar level. So if we add the complex quantity to its conjugate, so we're going to end up with real parts only. Added and divided by 2, there is a scaling factor here. So since z2 is exactly the conjugate of z1, when we consider z1 plus z2 divided by 2, there will be some cancellation. We're going to get rid of certain things, but let's see that in action. So here, so divided by 2 is the same as multiplying by 1/2, and we have here z1 is et. So the first contribution is et e to the I 2t times the vector 1 minus I, and then we have this expression et e to the minus I 2t times the vector 1i. So using Euler's formula, we can see how the first vector here takes this form. We're going to have to write a couple of steps here. This I squared being -1 minus I squared becomes +1. But here we have the first vector and the second vector. And what follows next, as we can see, adding these vectors implies we have to do that addition entry by entry. In the first entry, this term, the imaginary term, has opposite sign to this term, so those two terms are going to cancel, they're going to go away, and something similar will happen in the entry number 2, where the imaginary term involves cosine, so these terms are going to cancel. So what we're left with is, in the first entry, the only surviving terms are the real terms, and we end up with 2 times cosine of 2t. And for the second entry, we end up with 2 times sine of 2t. So this 1/2, this coefficient 1/2 is going to cancel with this coefficients of 2 in each of the entries, and then we can distribute that exponential of t, e to the t. So z3 has no imaginary parts. In fact, the first entry of z3 is et cosine 2t, and the second entry is et sine of 2t, but we see here that the imaginary parts have disappeared, and this is an implication of what we remarked first, in which we could, at a scalar level, represent the real part of the complex number by adding the number to its conjugate and then dividing by 2. So motivated by actually the other calculation, in which you can represent the imaginary part only by subtracting and dividing by 2i, we're going to define now a vector z4. We're going to define z4 as z1 minus this conjugate divided by 2i. And let's remember that we're also calling z2 the conjugate of z1, which is this vector et e to the minus I 2t times the vector 1i, right? So that's what we are involved in this calculation, z1 minus z2, that vector we just mentioned. We're multiplying really by a scalar coefficient 1 over 2i. It's multiplying et. We're going to factor et since that's repeated, and that here we have e to the I 2t times a vector minus e to the minus I 2t times a vector. So what we have to do now is to do some algebra, apply Euler's formula again, and simplify. So in this part of the calculations, one needs to be very, very careful with signs. Okay, these positive and negative signs, they require substantial attention. We are applying Euler's formula repeatedly. I think it's a good practice to keep this e to the t, this exponential of t, as a common factor. Hold it, keep it on hold there for a little bit, and we're going to add here similar terms, and in a similar fashion to what happened before, we're going to see that there are some terms here that will be canceling. For example, this cosine and this negative cosine, they are going to cancel each other. And similarly for this term with sine, negative I squared is positive 1 and I squared is negative 1, so this term is going to cancel with that term. So this would imply that z4 is taking form as this vector with coefficients 2i in the first entry, negative 2i, but that's where this coefficient 1 over 2i will be very convenient. So this will simplify these terms. These numerators are going to simplify with that denominator of 2i, or 1, the factor 1 over 2i, and so we will end up with c4 being on the first entry e to the t sine of 2t, and the second entry e to the t negative e to the t cosine of 2t. So the general solution without imaginary parts, or with imaginary parts equal to 1, the general solution with 0 imaginary parts is defined as, I'm going to call that u of t. Okay, perhaps I need some more coefficients here. I'm just going to call them c3 for coefficient times z3 plus z4 times z4. In other words, we're saying that this looks like constant times the vector this will take the form, because of our previous calculations, will take this form, and we have a constant C3 times this vector et cosine et sine plus a constant C4 times this vector et sine negative et cosine. And so this solution u of t satisfies the differential equation. It satisfies the differential equation. We're going to put on hold the information on the initial conditions, but we're working with this differential equation. So that solution u satisfies this. So we can write the solution u, newly constructed, as C3 et cos plus C4 et sine. That's for the first entry. The second entry would look like C3 et sine minus C4 et cosine. So it's not too difficult to confirm, to verify that this newly constructed solution that has zero imaginary parts actually satisfies the differential equation. And I say it's not too difficult because, well, in the mixture here we can say the derivative, a mixture of notation, I mean, you can say the derivative of u, okay, is obtained by differentiating each entry here. So the derivative of the first entry will look like C3 et cosine. You have to use the product rule here, plus C3 et product rule and chain rule at the same time, plus, and then now we have to differentiate this portion that's multiplying the coefficient C sub 4. And then we differentiate the other term, the second term, the sum, and obtain, again, applying product rule and quotient rule. So now we take the derivative of the second entry. I'm going to do that with a slightly different color, right? And so that's going to look like C3 et sine So differentiating the second term, the second entry, here's where again you have to be very cautious with the negative signs, right? So the derivative of cosine is negative sine, and there already is a negative in front of that expression, okay? So we can clean up the terms in the first entry and group the terms that have common factor of 2, and so the first entry would look like C3 e to the t cos plus C4 e to the t sine, and we can write this as minus 2 quantity, and that is C3 et sine minus C4 et cosine. You'll see in a minute why these terms are grouped in this way, and then we'll do something similar with the terms in the second entry. We're going to collect the terms that have a coefficient of 2. So the second entry would look like this: 2 times quantity C3 et cos plus C4 et sine plus C3 et sine minus C4 et cosine. So I'd like to point to your attention that they're rewritten in this form because of the way in which we had defined the solution u. So this first entry is what is going to be called u sub 1, and this second entry will be considered u sub 2. So we can now start noticing a pattern in which the derivative is written in terms of u1 and u2. You can notice that this term here is u1, this term in parentheses, this quantity, is u sub 2, here we have 2 times these terms, and this term parentheses is u1, and here we have another term which is u2. So in other words, we can express that vector, and lastly, that vector can be expressed or interpreted as the matrix vector product, this 2 by 2 matrix with coefficients in first row 1, -2, and coefficients entries in the second row 2, 1, multiplying this vector. You can see how this entry is u1 and this is the u2 entry. See, this is exactly what we would need to write, or exactly what we accomplish in verifying that this newly built vector u is a state variable vector that satisfies, okay, this vector has 0 imaginary parts, and it satisfies the differential equation du dt equals this matrix times u, which is exactly the definition of the problem that we were interested in.